My second year's algebra course was based on group theory. Its concept is central to abstract algebra, where other well-known algebraic structures, such as rings, fields, and vector spaces, can all be seen as groups endowed with additional operations and actions. The picture is the Cayley graph that encodes the abstract structure of a group. The contents are divided into four parts. First of all, groups and subgroups. The concept of a group structure and a given set is introduced. Subgroups are studied and the concepts of order and index of a subgroup are defined. There is a special emphasis on characterization of a normal subgroup. Secondly, homomorphisms and automorphisms, their concepts and the main theorems of isomorphism are explained and proved at length. Thirdly, finite abelian groups. They all are classified. Finally, zero theorems. Some of the most immediate examples, whose results are striking for its simplicity, are studied. From a point of view, the most important I learned was 1. Identifying whether the given set has group structure. Besides distinguishing subgroups in a particular group and understanding the mentioned concepts of order and index as a group. 2. Characterizing subgroups associated with homomorphisms. 3. Classifying finite abelian groups using the fundamental theorem that states every finite abelian group G can be expressed as the direct sum of cyclic subgroups of prime power order. 4. How to apply Taylor theorems to cyclic group orders with those theorems using resorts or small groups. One of the requirements for the term was to describe some application of group theory. I chose cryptography. For instance, the RSA encryption and decryption method is a direct consequence of Euler's theorem applied in a cyclic group. The picture is related to Caesar's cipher. It may also be interpreted as a very easy group operation. Although I have to recognize I was not very interested in this matter at the beginning, broadly speaking, I consider the subject was a nice study on symmetry. What I liked most was the final project that allowed me to discover such as interesting as well as common applications that even I could say I was delighted with group theory. Since then, I have a different and deeper view on puzzles like Rubik's Cube, identification numbers, some areas of analysis, public key cryptography, classical problems in algebra, and, of course, symmetry. I remember one of my schoolmates posted on forums, "Group theory is the basis of modern physics. By Norden's theorem, it is the abstract mechanism responsible for conservation laws, for example, the energy and momentum one, even in classical mechanics. In quantum mechanics, representations are even more important. The ones of a particular kind of group describe the difference between bosons and fermions. and other representations can also describe the possible orbits of an electron in a hydrogen atom. So, group theory can be used, among many other things, to predict the structure of the periodic table. Then, I realized how group theory also happens to be fundamental to many modern branches of mathematics. But I figure an application to things that people probably care about outside of mathematics would look better.